this lecture with some problems which are based on shock wave experience. So, yes, now let us go through this problem and I will explain the idea to analyze the problem. Problem here is there is a shock wave which is in the region of a elevated pressure, right? And this wave is propagating in the positive direction of the axis with a high velocity v. So it is given that at the moment of arrival of the wave, pressure is abruptly increasing, and the variation of pressure is given to you. That means if the pressure everywhere is P naught, as the wave arrives, the pressure abruptly increases to 2 P naught. And this dependence is plotted in the figure. The question is somewhat like this, that you have to find out the velocity acquired by the wedge immediately after the shock front passes through it. And there are some standard assumptions that the mass of the wedge is m, size is given, friction is neglected, velocity acquired by the wedge, that is assumed to be much lower than the velocity of wave. I'll use this assumption while solving the problem. So if I interpret this problem from the front side, it can be observed like this. So this is my wedge at t is equal to 0, kept on a frictionless horizontal surface, and the pressure everywhere is P naught. So as the front reaches this location and it is moving with a velocity of v, we can analyze the problem at a general instance. Let's say I'm presuming my wave front reaching the front edge of the wedge to be t is equal to 0, right? So I'm trying to analyze this problem at a general instance, which is t is equal to t. Let's see. So at t instance, there will be a section. So let me treat this height as a, b, the cross dimension that is given as c. So in this wedge ABC, at t is equal to t, there is a point P up to which the wedge has been exposed by the elevated pressure waves. And because the pace at which it is moving, v, that is assumed to be large, by the time, that means the t, that will be treated or can be treated as a small time gap. I mean, in this time span, we are presuming that the impulse in between is large, but delta t time is so low that the velocity is yet not being acquired. Yeah, मतलब वो ये presume कर रहा है that exposure of this signal is up to point P. I am talking about pressure to be P naught here. And why I am not showing any pressure on this section? Because we know that if pressure on both the sides is same, the net force on this section will be 0. So basically what I'm trying to say is pressure here throughout is P naught, right? This section also pressure is P naught, and this part also the pressure is P naught. So this section, like A, P, and whatever this point is D, this section is not experiencing any net force in the horizontal direction. Although on the section, this section, here the pressure is 2 P naught, right? In this section, the pressure is 2 P naught. And effectively, if I want to look into the force on the body at this instance, that I can find out. That is primarily because of the force on the section BP and the section CD. So that will give me the effective force in the rightward direction at time instance t is equal to t. This is the section up to which it is exposed, and the velocity with which it has traveled, that has been given as v. So indirectly I can say that the shock wave front has traveled a distance which is primarily this distance, and that is basically vt distance. Let us take this angle as some theta, we'll take care of that afterwards. If I want to just express the force function, I'm directly saying if this force is somewhat like F1 and this section is contributing a F2, so we are clear that our effective rightward force is coming out as some F1 sine theta minus F2. And it seems like F2 here the pressure still is P naught, which I have represented by yellow color. So that is P naught into that area. So you understand this is Vt tan theta, right? and the depth dimension here is C, so multiplied by C. So this is the face area, right? So this much is your F2, and what is this term? F1 sine theta. So keep it as such, sine theta term, and F1 will come out as the elevated pressure, which is 2P naught into the face area here. So it is, this was Vt. So Vt upon cos, so write it as Vt upon cos theta, and multiply this term by C, the depth dimension. Just carefully look into that expression. When the elevated pressure pulse has spent a time t, which is very, very small, over the wedge, the effective force which that pulse, the pressure pulse, is exerting on the wedge, that is in the rightward direction, and that much is the force. Check the expression again. I have just taken the pressure here, 2P naught. I've taken the section length, which is Vt upon cos, the depth dimension C, and the component. And now what I'm trying to say is, if this much is my rightward force at T, effectively you wanted to find out the velocity, I could have directly said that if this is F net in the rightward direction, I could say my impulse F net dt, right, for the tenure T is equal to 0 to T is equal to, so basically it has to travel B. So B divided by the wave velocity, let's say wave speed, in this case, which is V. This will be the effective impulse that we are going to impart to the wedge. And that should be the change in momentum of the wedge. So that should equal to m into the velocity that it will acquire. Let's say that is u. Initial was 0. So I think if this is the second equation, and F net मैंने यहाँ लिख दिया, this is the first equation, we should get the value of u, velocity acquired by the wedge. But just let me finish it off. It will be equal to mu. U is something which we need to find out. An integral F net dt, that can be easily written. So except for these constants which we are getting, let us just try to express this even in an easy way. It is Vt P naught. So it is P naught Vt C tan theta. Just look into this expression. It is 2 P naught VTC tan theta minus P naught VTC tan theta. So P naught VTC tan theta. So I think the result is P naught VC tan theta into T square by 2. So by 2 and T square, that will become BYV the whole square. Now you have to just solve this expression and you'll get the value of U. Obviously, while the wavefront is crossing the wedge, I'm assuming that the wedge is not moving. Differentially, it will move, but that speed is high, so it is assumed to be like a complete impulse. Indirectly, you can say that we are treating this impingement of sharp elevated pressure pulse on the wedge like a sharp impulse on the wedge. After that, it is a simple calculation and you will get your result. Right. So that was one problem where we can observe the effect of pressure pulse at a particular location. Now, the same concept of pressure pulse can be perceived in another way. You can just check this combination. Let's see, if I want to eliminate that factor of sudden impingement, अगर उसको थोड़ा सा हटा दें, how do we perceive the problem? So let's just observe this problem. Again, in this problem, there is a plane pressure pulse. This is the pressure pulse. Let's understand. They have given you a graph of P versus X at some time instance. Let's say T is equal to 0. And the peak pressure here is 100 pascals, right? That is 100 pascal. The peak pressure, that is above the mean pressure. All those things are standards. The point is, by the wall, this pulse hits the wall, it gets reflected. And while it is getting reflected, he's saying the pressure near the wall gets doubled. I'll explain this point also, why he's saying this. So I'll come to this point on whether it was required or not. He's also saying the height of the wall, that is 2 meters, and the width is also 2. So depth, dimension, height, that is 2. So we'll take care of that. He is saying that there is a detector on the wall which can record a minimum excess pressure of 16 pascals. So that recorder can sense any excess pressure which is above 16 pascal. The point is, if this sound signal or a pressure wave travels along a medium and hits the wall, right? This is the shape of the pulse. Then we need to answer these problems on the basis of that supposition. So let's see how to observe the question. The first problem says that what is the first time the detector will record the pressure pulse? Now we can see that the pressure, the starting point I and the ending point is, the starting point of the pressure pulse is at a distance of 80. And whenever this pressure pulse hits this point, right, that cross section, that end point will behave as the pressure antinode, right? So by the combination of the pressure wave which is reaching that point and the one which is getting reflected and superposition of those two, he is already telling me that the net pressure there becomes doubled. So we want to observe a pressure pulse, and for that minimum excess pressure is 16. So basically I'm just interested in something which is like 8 pascal. So if this point, I mean, when the signal of 8 pascal will reach this point, by virtue of reflection at that interface, it will become 16 there, and 16 will be detected. So indirectly, you just want to ensure that 8 pascal reaches this point, and the distance for this is like 80 meters it has to travel, plus whatever distance it has to travel for 8. So for 100, like it is 50. So 4 meters it has to travel extra. So it seems like 84 meters is what my traveling pressure wave has to travel for a detector to detect that pulse there. And it is traveling at a speed of 400. So it seems like this much amount of time it will take. That is the first part. Secondly, he says that what is the time span for how much time the detector will record the pulse. So fine, I mean, if the observation there, which has reached the incident wave, is ensuring that the pressure which is reaching there is 8 or greater than 8, then it will keep on detecting the pulse. So just you have to look into these 2 points. I mean, that point and this. And whatever is this gap, I mean, while it will travel this much length along the pressure wave, the detector here will keep on detecting the signal. So if I just try to find out this length as such there, so 46 meters is what I am getting from this side. 4 meters I got there for 8. So 46 is this, and remaining is like same. So for 8, this is simply 8 here. So this is 92 more, and it is traveling again as at 400. So this much amount of time, the delta t time. This value here is 8. So this will be 8. So this will be 92. So this total length as such, which I have shown here on the board, that becomes 92 and 46, and it is traveling at this rate. He also says, find out the maximum force which is applied by the pulse on the wall. So the maximum excess pressure that reaches there is 100, and it will become 200 after superposition of the reflected one and the incident. And the face area of that wall is 2 into 2. So that will come out as the third part. And the last segment, here it talks about the total impulse which is imparted by the pulse on the wall. So for this, we can do one thing. I can draw, so to solve this, it's better to draw the force applied by the pulse on the wall versus time signal. Let us try to draw this. Let's see how to Observe this. If I look into the pressure which is reaching, the first time the pressure wave reaches here, after traveling 80 meters, I have treated that time, that time t will be actually 80 by 400. Treat that as your new zero, because only after this instance, this I am treating as t prime is equal to 0, this instance. So I am drawing graph versus t prime, right? T prime is equal to 0 is the instance when the sound pressure pulse is reaching, is just hitting this wall, right? So forget about this 80 upon 400. Now what happens? So with respect to distance x, it's a linear pressure pulse, and x and time are directly proportional because wave is moving with a constant velocity. So with respect to time also, it will be linearly proportional. And over a period of 50 meters, so that means t prime will be equal to 50 divided by the pace with which it is traveling is 400. So that is 1 by 8. Till 1 by 8 seconds, this signal will reach, and maximum, the pressure that will reach there is 100, and the face area is 4. So it exerts 400 newtons, but it is doubled. So this graph becomes 800 newtons. The maximum force that it will be exerted, and force versus time will be linear. So I've converted this versus x graph into something which is linear with respect to time. And quite evident, after that also it is linear. So directly it will be 0 pressure. So force will also be 0. Only thing is that t prime will be equal to 1 upon 8 plus the additional time that it will take. And it will take 100. So 100 meter divided by, again, that 400 meter per second. So basically a factor. So 1 by 8 plus 1 by 4 second, that is the final instance, right? After that, it will be 0, it will be reflected back. So this is what is the force versus time graph, which is the force exerted on this wall because of the pressure pulse. And you want me to find out the total impulse. So simply I have to find out the area under the graph. So the answer to this question now is simple. It is half of that term, which is 1 by 8 plus 1 by 4. And then the second value, which is 800. So in totality, this is the momentum Newton second, or the impulse imparted by our pressure wave onto the wall. So again, there were few things which we need to be careful about while solving this problem. And you understand this thing very clearly, that this was an interface of rarer to denser. And that's why when I said that there is a pressure pulse, I knew that this interface will behave like an antinode for that pressure pulse. And that is where he has given that data also, that the pressure at that place becomes double, right? Because of the property of that interface to behave like an antinode. As yesterday also I discussed, by Stokes' theorem, we can justify that point. Now we will try to club a combination where I am putting up both the things, including the variation of intensity in the problem. So let us observe this question. There is a point isotropic sonic source, which is having a power of, that source is having a power of 1 milliwatt. It emits sound of frequency 170 hertz in all the directions. So there are few things, and basically I'm interested in the B part of the problem, which is there are few things which we need to analyze. In the first part, they have just said that you have to find out the distance of a point from the source where the loudness level is this much. We'll calculate this. Let's focus on B part first. Here he is saying, if it is known at some moment t is equal to 0, the displacement of air particles at a point 4 meters away from the source is A. Just observe this carefully. At t is equal to 0, you are talking about the displacement wave. So displacement of air particle, which is whose mean position is 4 meters away. So if I just draw this setup. It's like this point is behaving as a point source S. There is some power it is emitting, let's say 1 milliwatt. Then you are at a distance of 4 meters from this point. And what we are trying to say, this I'm drawing a sphere, which is the equilibrium layer, or you can say the mean position of all the vibrating particles, which are lying at a distance of 4. And you are saying the amplitude at this point is 2a, but that particle which we are observing, so so I'm just using different color to show the S wave. So I'm saying at this place, the maximum displacement which we can go on either side, this is 2a, this is minus 2a. But my particle whose mean position is here, at that moment it is at a distance of a. It is at a distance of a with respect to the mean. That is good. He is saying find the displacement of air particles in terms of A at a point which is 55 meters away from the source. So he is now talking about a particle which is 55 meters away from the source. We want to write his displacement from his mean position, right? And again, at the same instance, and remember, this green diagram that I have shown, this is at t is equal to 0. And he wants me to express this displacement of the S wave at this location, whose mean is at a distance of 55, at the same instance, t is equal to 0. Now, the first thing is, he has already given me the amplitude at this place. So I need to first find out the amplitude here. And with respect to the amplitude, if I can analyze the phase properly, I can find out the lead in phase that this particle has got, whose mean position is here. Then we can easily represent, solve the problem. So amplitude we need to find out. So it's simply I can write that intensity. So you can simply say that intensity there is like P upon 4 pi into 4 square. And that is proportional to 2a the whole square, right? And similarly, if I want to write intensity there, so it will be the power upon 4 pi 55 p whole square. That will be proportional to, call it a prime, as we'll see, that's proportional to a prime square. Let's divide it. So 2a upon a prime, that will be equal to their squares ratio will be equal to 55 upon 4 the whole square. So basically that a prime comes out as 2a into 4 by 55. 55 by 4 comes out as 2a upon a prime. A prime is 2a into 4 by 55. So 8a by 55 comes out to be the amplitude at that place. So that is known to me now. And I will draw its phasor with respect to his amplitude at that location, right? So now, at t is equal to 0, so I am talking about a distance which is 51. So over this distance of 51, so part difference delta x being 51 from this point to this point, again at t is equal to 0. If I want to write that phase difference, delta phi, that will be equal to, it is phi by lambda into delta x. Now let's look into all the calculations carefully. This value is 51. Lambda in this problem, that we can find out because frequency was given and Vs was given. So this comes out as 340 on 170. So this comes out as 2. So this is 2. So practically it is 51 pi. So basically the particle, let me say that this position is, let's say, C. Particle jiska mean position is at C. And this is particle whose mean position is D, is leading by a phase of 51 pi. And now directly we can say this. So there is a factor of pi actually. So now if I look into his phasor, like he was 2a. So practically, if you look into this diagram, just to explain that point, it was someone whose amplitude is 2a and he was located, although it was not given. So when he said that it is at A, it could have been like this, that it is at A, it is moving upwards. So phasor could have been here, or there's a possibility that this was moving back. So phasor could have been here also. I'm talking about the case where amplitude was 2. Irrespective of that, I knew that this angle directly was 30 degree. So you are making a new phasor, which is at an angle of 51 pi higher. So practically under both the situations, it will be vertically opposite. So either my answer is here in this quadrant, or it is here. Both the situations, it is making an angle of 30 degree with the horizontal down. So and his amplitude is A prime. So practically the position, the answer to the problem should be negative sine 30 of the new amplitude. So A prime sine 30, right? So actually it should be minus A prime divided by this phasor, right, having an amplitude of 2A and located here, and the other guy which is leading in phase by 51 pi. So we have drawn a new phasor which is 51 pi ahead of this one. So either here or here. Under both the situation, the projection of that will be here, so downwards. So, and what is the new amplitude? So we have to write, this was with respect to 2A, now with respect to A prime. A prime you already know. So it should come out as minus A prime upon 2, and that A prime term is 8A by 55, right? So minus 4A upon 55, that should be the position of that point. So that was the first problem, and baki sab diya hota, displacement of particle to be positive if it is away from the source, that I have already considered. As far as this part is concerned, this is not a big hassle, just you have to use a formulation, just a sub part of this problem. So it is 10 log to the base 10. You have to just use I upon that term, I naught, right? I upon that term, I naught. So this value is 10 raised to the power minus 12. We will find out the intensity and then just write it as P upon 4 pi R square. Get the value of R, you will get your result. Power is known to use the SI. So mainly in this problem, he was trying to correlate. Now you understand these problems can be converted into problems of cylindrical symmetry also. So those things can be done. But basically phase movement has been analyzed. And you understand, here I was talking about the displacement wave. The same information can be reinterpreted in terms of movement of the pressure wave, right? With the appropriate phase difference of, in this case, similarly, I mean, here the complete analysis of phase has been done with respect to the displacement wave. If you want to analyze for pressure wave also, in terms of delta phi, the analysis remains the same. In terms of phase difference, the analysis remains the same. The phase difference analysis, rather, we can say, that will remain the same. So that was the third combination, again related to a pressure pulse. Yesterday also I discussed about the same, but the direction of the flow of energy, the rate of flow, these things were not being analyzed. So let us just read this question number 15. On a string are two successive instances of time. So the first one is at time instance t is equal to t1 is equal to 0. Then there is some instance t is equal to t2. ABC are points on the string. So is the maximum displacement amplitude of the standing wave. So you understand that. They are their peak positions that is given to you. Table 2 talks about the observations about the net mechanical energy for the time interval between T1 and T2. So now we need to answer this problem. We understand that we are analyzing this problem from 0 to T by 4, right? And he's talking about these three different cross sections, A, B, and C. First few points that we can directly answer. First, he is talking about A cross section. He says the kinetic energy of this element is increasing at the time instance between T1 and T2. इसमें कोई fight नहीं लगता because it seems like this particle A is moving towards the mean position. Seems like P seems to be correct, not a hassle. Now there are three different points he is making. First, the flow of energy is towards right at T1 time instance. True. Energy is moving in the leftward direction at T1 from this point A. From T1 to T2, energy will cross. So obviously, S option cannot be correct. And now it comes to Q and R to analyze in which direction is the energy crossing. So while these particles, now lot of ways you can observe it. Try to think the way you find it to be fine. For me, the observation is somewhat like this, that from T1 to T2, the potential energy at the node is getting dissipated through this section from this point to this point towards the antinode point, and B is the antinode point, so it will be gaining the kinetic energy. So it seems like that energy is crossing towards the right direction. So it is going towards right at this instance. T1 seems correct, so Q seems fine. Left is obviously not an option. If you talk about B, kinetic energy is increasing, that seems perfectly fine. Energies Q and R, I'm not convinced. S seems fine. That energy is not crossing through this cross section ever. The reason is very obvious, that whatever happens from the left hand side, the physics of the problem from right hand side is identical. So you understand, by logic also you can say that crossover is not possible. Otherwise, the nature on either side of antinode will be different. So that behavior cannot be different. And C, I think all of us understand, the behavior is exactly opposite to that of A. The only thing being that energy is moving in the leftward direction. So P seems right and R seems right. Rest options do not work. So I think with the help of the idea that I have discussed with you yesterday, that question can be easily taken care of. All right, now let us superpose the idea of Doppler effect with that of a standard standing wave combination. So let's read this combination here. ABC is a cylinder ABC that consists of two chambers 1 and 2, which contains two different gases. Wall C is rigid, but walls A and B are having thin diaphragms. And he says there is a vibrating tuning fork which is approaching the wall A. So let's say this tuning fork is moving rightwards, approaching the wall A with a velocity of 30 meters per second. That is good. And he is also saying that the air columns in chamber 1 and 2 vibrate with minimum frequency such that there is a node, displacement wave node at B, an antinode at A. So displacement wave. So I'll discuss this in terms of S wave only. And he has already said that S wave node is here and S wave antinode is here. And obviously the wave which will get refracted in that region BC, for them we know that C will also behave like a node. It will also behave like a node. We will take care of this point. This we will try to find out what he is trying to say. 1 and 2 vibrates with minimum frequency, right? So you have to find out the fundamental frequency of air column. We'll see that. And definitely I'm interested in the frequency of the tuning fork also. Let us first find out what is the frequency of the tuning fork in this problem. Sound velocity in the gases which are filled in the first and the second chambers, that is given 1100 and 300 meter per second. That we'll see. So first point, if we talk about the S wave with this being antinode and this being a node, so for this length L, basically I should say 0.5 meter behaves like. So this is like quarter system. You understand that? So I'm calling it as 1, 2. So lambda 1 by 4 or 3 lambda 1 by 4. So odd multiples of lambda by 4, seems like 1 lambda by 4, 3 lambda by 4, so on, something of this sort. And when we talk about this 1 meter, this is lambda by 2 integral multiples. So lambda 2 by 2 or integral multiples of that, like 2 lambda 2 by 2 and so on. So we'll see. And getting a fundamental, Abhi, this won't be the frequency of tuning fork, but if this system is in its fundamental mode, I am basically searching for a frequency for which both the conditions are satisfied. Right. So indirectly, the frequencies which are possible here, F1 possible values are lambda 1 possible values. So they are coming out as 2 or 2 by 3, 2 by 5, so on and so forth. Right. These are the possible lambdas. And frequency. So V1 is given 1100 by possible lambda. So 1100 by 2, 1100 by 2 by 3, or so on and so forth. Like, you understand. So these are the multiples which are possible for F1. Similarly, when we talk about this F2, here lambda 2s which are possible are 2 or 2 by 2. These are the values which are possible, 2 by 3, so on and so forth. And so possible frequencies here for velocities being 300. So this is 300 by 2 or 300 by 2 by 2 and so on. Now simply search for a value which satisfies both the equation. So the least F min, right, which is a part of that setup, that set and this set both. What is that value coming out to be? Because these values are like 550, no? So 1100, 1650. There also you are getting multiples of 150, like integral multiples of 150, and these are all odd multiples of 550. So you can see that 650, 1650, that is the third multiple, that works there also. 11th multiple is come. 1650 comes out to be the least value where both the conditions are satisfied. And now he said, now comes the Doppler effect. He talks about the frequency of the tuning fork. So basically this cylindrical system is like a observer which is basically in a state of rest, and he is moving, the source is moving towards the observer. So when you say 1650 is the observed frequency by this observer, which in this case is the cylinder. So I should have written 1650 to be equal to, if the actual frequency of this tuning fork was some F or nu, whatever you want to say, this was some F actual into, then observer was at rest, speed of sound that is given as air 330. So 330, 330. And source in this case is moving. So there should be a factor of minus 30. So actually, the frequency of the B part of the question, that can be answered by F value, which will come from that 1650, which we are observing. So there are 2-3 things which we are trying to do in this problem. First of all, through the boundary conditions, we are trying to find out the possible lambdas or the frequencies, for the system to resonate, and same for the second tube. And for them to have a common frequency to generate a standing wave pattern in both the setups, both the cylinder, we found out there will be few frequencies for which both the conditions, all the 3 boundary conditions are satisfied. And out of those possible frequencies, the least one is 1650. But 1650 is something which is observed by the setup. But that sound signal was himself moving towards this cylindrical system, which was at rest with a speed of 30. So I've just used the Doppler relation. I can definitely do few things with wind moving. I can take this guy, take it at a general theta, and let it move at an angle theta also. So all those ideas can be utilized here to make this problem more cumbersome. But that is how we solve this problem, get F. Now, the first part also was the fundamental frequency of air con. I think that is not a hassle to any one of us. You can find out all the possible frequencies of oscillation of the left as well as the right con. So you understand, I think you all understand the utility of this point and how we are going about solving it. Now, whatever I have done in this problem, in terms of Doppler effect, let me just try to extend it into some different combination. I mean, before I take up problems which are based on Doppler, just take up this idea. At times they give you, when we talk about the concept of beat or beats formation, we can always give you any number of signals, any number of frequencies actually. Just in this example, you see that they have given you 3 signals of frequencies 399, 400, and 401. Actually, the theory doesn't stop up to this point that they will give you 3. They can give you any number of signals which are being clubbed together. If they say that find out the beat frequency, that means what kind of pattern is being formed there. So if I look into this problem, let's say I'm sitting at a particular position P, and I want to observe the displacement wave, which is reaching the observer here. Let's say these 3 signals are reaching there. So you understand that in this case, it is quite simple because it's like A sine frequencies, like, fine. So 2 pi into 399t plus some phase phi 1 is reaching. The second guy has got A sine 2 pi into 400t plus some phi 2 that is reaching from the second person. And similarly, from the third person, it is A sine 2 pi into 401t plus some phi 3 is reaching. Right. So we understand that when the signal is reaching that location, it is actually some A sine omega t minus kx plus phi. But because we are analyzing the formation of beat at a unique position, so for that particular x, those kx terms will be clubbed in these phi's only. So practically, you will only have a sine omega t term, plus or minus whatever it is, which is again compensated in phi with some constants. These are phi 1, phi 2, phi 3. So actually, for me, any number of signals getting added there are basically additions of SHM, superposition of SHMs, multiple SHMs at that point. Now, the only concern is when he says find out the beat frequency. Now, what I'm trying to observe is, can we convert the summation, superposition of these signals into a pattern which is similar to that of beat? And when you talk about beat formation, you talk about oscillation of signal, right? Oscillation time period of signal, along with the oscillation of amplitude. And the game is, the idea is that oscillation of amplitude happens at a very slow rate in comparison to the oscillation of the signal itself. And that is where we draw the boundaries and we perceive these things as beat. That is where we call the concept of beats comes into picture. So actually, the oscillation has to be there. So, and we want to convert this equation as, if I convert this becomes A. Just try to club it. So effectively what we are trying to say is, I'm going to club this term and this term together. So we are going to get a term which is of the pattern of sine 2 pi, because that will add up to sine 2 pi into 400t plus minus whatever constant. And then a core term, a sine or a cos term with a time period, because in these 3 terms, this will come out as a common term. The second term, sine or cos function, which you are going to have, plus minus constant, you will have. In this case, that time comes out as 2 cos 2 pi t. So it doesn't matter actually. 2 cos 2 pi t plus minus whatever constant. So what I am trying to say is that frequency of 400, and then there is a frequency of 1. So actually what we are trying to say is the time period of both of them. One is the amplitude oscillator and which one is the actual signal oscillator. If this is very, very less, right, this omega is large, which in this case is 400, then the second guy will actually define the time period at which the amplitude is going to oscillate. And in this case, it is very clear that the amplitude oscillation is like 1 cycle per second in this case, because that frequency comes out as 1. And that oscillation of 1 cycle per second for the amplitude, what I have told there, I just accomplish it completely. This will become that 1 cycle, right? This will become that 1 cycle.
So why is it coming 2 pi 2t?
You're adding
for the entire
for that function. I'll explain. For that function, if I get this time period t1, right, which will be large, I will explain, in comparison to t2, and t2 in that problem should be a smaller value. If we can justify this, let me explain the theoretical part and I'll come back to it. So, hoga kya? In that case, what will happen is this structure for if I find out t1 and I justify that t1 is large in comparison to t2, then that amplitude oscillation, right, will let your wave or the signal oscillate between the boundaries. And then it will be very easy to define this pattern to have a similar nature as that of beat. And if we get this, then the beat time period, I mean, like in t1 seconds there, you will have 2 beats which are being formed. So number of beat frequency we can find out, number of beats per unit time. So ultimately what I have to search for, I have to search for a t1 and a t2. And I am just searching for this oscillation, right? This starting point goes to this point. This time period I am searching for, which I am looking forward as t2, and this bigger time period as t1. If we can just find out t1, t2, if we can justify that relation t1 large in comparison to t2, then beat frequency is fine. So for every second, it is 2 upon t1 beats. So 2 upon t1 beats per second, and that will define your beat frequency. So that is the theoretical aspect of the problem. Now I want to come back to that idea. So now if I give you these 3 signals, now if I take up these 3 signals, yeah, and we try to club the first and the last ones, let's see what we are getting. So I'm getting, I will rearrange my phi's also as and when required. But let us first try to generalize this, as someone was asking. So I'm just clubbing the first and the third terms. Let's see what we are getting. So I am just using a sine a plus sine b, twice of sine of a plus b by 2. That term is 2 pi into 400t plus phi 1 plus phi 3 divided by 2. And cos of getting as a minus b by 2. So what is that? 2 pi t, and I think it is 2 pi t 401 minus 399, that is 2 upon 2. So that term is fine. And plus it is phi 3 minus phi 1 by 2. Now I want to club this with the second term which is available, which was a sine 2 pi into 400t plus phi 2, right? This is what we want to analyze now. And now I can convert this signal into this pattern with some conditions being superposed. Now think about it. So we understand it very well that phi 1 plus phi 3 by 2 being equal to phi 2. There are 2 ways. I could have, this is a general format that I have taken where I can superpose some conditions. Otherwise, also, like in this problem, I know that this term should be common in the signal. So what I'm trying to do here is, let me take subcase 1 just to explain the concept, and then we can solve more combinations. Subcase 1, if phi1, phi2, phi3, they were made equal to 0. This is not something that we will do. The problem setter has to specify that condition for the formation of beat. In that situation, what will happen? Under that situation, your net equation will convert into what? Sine, so it is like A sine 2 pi 400t, because 2 pi into 400t, that term is common. Then what is that we are getting? So A sine 2 pi into 400t and 1 plus 2 cos, it would have been 1 plus 2 cos 2 pi into t. I mean, this is one case where you can easily observe that the core oscillation, now what I am saying is, your oscillation is this signal, sine 2 pi into 400t. So the frequency of 400 hertz is for the basic oscillation. So 400 cycles per second. High dynamic rate of oscillation is happening. And A into this term I am perceiving as the amplitude as a function of time at that particular x. So you can understand that this is like A plus. So A is the mean level. And with respect to that mean level, the oscillation is happening with a value of 2A above and 2A below, with this term cos 2 pi t is 2 pi into 1. Phase difference of pi by 2 can always be considered. So you understand that the mean level is different. With respect to the mean, the height is different. But the oscillation is happening at a rate of 1 hertz. That is 1 cycle per second. So you understand that in 1 second, this amplitude, you all can draw, this amplitude basically oscillates once in 1 second. But in the same time span of 1 second, the core oscillation is of 400 times. So 200 in both the brackets, you can simply say that 200 oscillations happen everywhere. So you can understand, we understand very clearly, the higher is the difference between these two frequencies, the better beat pattern is going to be formed. Because all of us know that while we are analyzing this, the frequency, the two frequencies should have such a large difference that the pattern, the wave pattern is restored. If amplitude starts varying in a dynamic manner, then the actual core pattern of the signal cannot be restored. The signal nature. So generally, how do we say? In the interval, the amplitude changes. In that small interval, when amplitude even changes by an insignificant amount, in that interval also, you should have one or more than one cycles in that patch. So that's why we say theoretically, the difference of the two frequencies should be as low as possible when you define the beat frequency. So that is the first case how I have written this, the term how I have written this, that I have explained 1 plus cos of that term and this term separate. Now you understand that depending upon phi1, phi2, phi3, such a pattern can be formed. And indirectly what I am searching for is any constant sine cos of some constant t, and then again sine cos of some constant t, and with that frequencies having a large difference, okay, higher order difference between the frequencies. So basically, they are not mentioning this, but they are saying find out the beat frequency. So basically, they are presuming that beats are being formed. So I've just explained that for a simpler combination. Obviously, there are other cases also when beats can be formed. If one term gets common, I mean, this phi2 and phi1 plus phi3 by 2 are either equal or they are at a difference of integral multiples of 2. Rest, the second term can always be taken care of. That is
Recording in progress.
Sorry, didn't get you. What do you say?
Yes. So in this question, the beats question that we discussed, the beat frequency will be the inner term, right? 1 plus 2 cos term. And what was the condition saying that the frequency of the amplitude should be higher than the frequency of the inner one, is it?
The condition should be such that the two frequencies should have higher is the ratio between the two frequencies. We can never specify an exact number for that, like it is like of order of 10 or of the order of 100. But we understand that higher is the ratio, the better is the beat frequency, beat pattern.
Okay. And so what exactly do we mean by a better beat pattern?
I'll explain that. If this difference is not large, it is a distorted signal. Actually, the problem is the nature of a signal or a wave is actually stored in that pattern only. I mean, the pattern, the pressure pattern, everything is stored in the nature of the cycle of the signal. So if you don't even give me that time, so by the time I am oscillating once, your amplitude is changing in a dynamic way. So practically not even a single cycle is completed. So then we will say that it's a random combination. It's some combination, but that is not what we called upon as beat pattern.
Right.
So that is, so people say theoretically that at least one signal should be complete. Obviously, we understand that more are the number of signals which are accomplished fully before the amplitude changes, the better will be the beat pattern. That is all. And that question, question clarifies one idea which I was more interested into. That was, it is not about that formulation of Newman, F1, F2 and beat frequency being F1 minus F2. That is very crude principle. Technically, that is not the way how we should teach beats. Right. What we should try to tell to students is, a person is standing at a particular location, any number of signals are bombarded on him. So if his ear is the screen or is the observation point, then all these pressure waves or the displacement signals which are reaching that place, they are basically getting added. And if that signal can be perceived upon or written like a core oscillation with the amplitude changing with time at a very gradual rate, then a pattern is being formed which is called upon as a beat frequency pattern. So it can be formed by 4 signals, 5 signals, whatever, if that can be mathematically converted into this formulation. So that is all.
Oh, thank you. Thank you.
Fine. Okay, let's move on to this problem where some 2D element is also involved. Let's read this. There is a sonic source that is moving in a circle of radius. Is a sonic source moving in a circle of radius 10 meter. Fine. So this is the signal. Radius 10 meter. It is emitting sound of 1000 hertz, right, while it is moving. It is moving with a constant speed of 110, fine, and speed of sound in air is 330 meter per second. Now he says there is a stationary detector which is located at a point 20 meter from the center of the circular path of the source. So maybe stationary detector in the same plane. Okay, fine. In this plane only, from 20 meters from the center, right? There is a detector which is fixed here. Now suppose the detector, which can detect only waves whose frequency is less than 1000 hertz, right, remains idle during a time interval delta t1 in one revolution of the source. So his question was that we need to find out delta t upon capital T in this problem. And I'll also try to derive that term which I was telling you. First, we'll complete this. So what are the important parameters? Like this is 10, 10, radius is 10 meter, distance here is 20. Is traveling, that point source is there, is traveling at the speed of 110. Now the problem with these questions and what should be the right idea, I'll explain. In this problem, while I will solve, what I will do is, I'll simply look upon the instances when the frequency which he is observing is less than 1000 hertz. So all those instances when frequency that he is observing is less than 1000 hertz. So That's what I'm saying. This problem I'll solve and then I'll come to the core explanation. What should we do? In such problems, we are just drawing a tangent to this curve. We are simply saying that while you are moving from A to B, in these instances, for these instances, all the frequencies that he will observe may not be at the same instance after some time. That will be greater than 1000 hertz. So for these instances, that guy will remain idle. So simply while solving this question, what we people do, delta t for which it remains idle. Na? So what are these angles like? They are 90, 90 here. That distance was 20. This was 10. So 30. This will come out as 60, 60. So this is like 120 and then becomes 240. So basically, I mean, 2/3 of the time period. So it seems like 2/3 it remains idle because 2/3 it observes less than 1000 and 1/3 it observes greater than 1000, but it can only detect less than 1000. So it remains active for this interval and it remains idle for this interval. Now comes the concept. In any such problem, there is one hassle which we should always take care of. That is, I'll explain it this way. The thing is, if there is something that we are, if there is a detector here, right, and he is also moving with some speed, let's say Vd, right? And then there is some source, and I'm drawing a situation at t is equal to 0. Let's say I say that this distance is L1 and this distance is L2 and source is moving with a speed of Vs and this is the instance t is equal to 0. Now, in all these problems which we are solving, we are actually assuming in 2D problems, we are actually assuming that the frequency is very high. I mean, frequency is high means, that means while I'm crossing a particular position, during the instance when I cross it, I emit a lot of complete signals from the same location. Otherwise, the concept is all based on kinematics. Otherwise, how we should have written the Doppler effect? The thing is, if I say that, what is the apparent frequency? If somebody says, what is the apparent frequency? Assuming that mu frequency or f is large, still while you are writing the apparent at this instance, maybe at t is equal to 0, what is apparent? So how we solve these problems? We will say, fine, this is the instance when he is here, but the signal that detector must have received at this instance was something that was being sent for him some time back. So I'll go to some, if this is t is equal to 0 position, I'll go to some time instance, which is 0 minus delta t, and I will let my source travel a distance which is Vs delta t here. He will reach this point. So I'll take the position of source at t 0 minus delta t and position of detector at t is equal to 0. Source at 0 minus delta t and detector at 0. And then what we generally do in while writing such equations, we will say from this position, obviously we know that when the source was here, detector was somewhere else. But while solving problem, we will say from this position, presuming obviously source would have emitted signals in all the direction, and for this location also, he would have emitted something. So if I am writing the apparent frequency observed at t is equal to 0, observed at t is equal to 0, I am actually writing it as actual frequency which is being emitted upon some parameter, speed of sound in still air c. And with respect to this diagram, I am just writing, if this angle is theta here, 90 minus theta, this position is also 90 minus theta. So we are taking observer or the detector as Vd sine theta term there, right? And here for the source, we are taking, this is Vs. So we are taking that term as Vs cos theta. And this is increasing the frequency and is going away. So that is decreasing minus Vd and theta. That again, I'll change this equation. But this is how we generally solve the problem, assuming that frequency is large. If this frequency is large, then at t is equal to 0, to write the apparent frequency, we'll use this equation. And all the parameters must be known to you. And then I have to write a theta term. So I could have generally said where tan theta is L1 upon that L2 plus, there are a few things which I need to eliminate. This is my first equation. This is second, L1 upon L2 plus Vs delta t. And all of us understand that in the third equation, the distance that the source has traveled in delta t time from here to here, that Vs delta t, is also the same time in which a sound signal has actually traveled from this point to this point. So in this triangle, this distance should be written as C delta t. C I am treating as speed of sound in stereo. So that the third equation that I have written is also helping you out, because there is again one relation. So you can, somebody can say that gives me sine theta equal to L1 upon C delta t. Technically speaking, L1, L2, those parameters must be given to you. So this second and third will help you find out theta and delta t, right? And once we know this, we solve for this. Even while we compensate for that delta t, at times we know that if the signal is traveling, I mean, C is large in comparison to Vs or Vd, even this point, this delta, Vs delta t will become very, very small. And under that consideration also, at times the people solve the problem, but that is something which is dependent upon the data given in the problem. This is the ideal way of solving, still with a limitation. And the limitation is, again, the point that I was explaining earlier. I'm assuming that this is high. So somebody can say that when you write the apparent frequency with respect to this position, you are assuming the complete signal to be transmitted from here. So again, I should say the frequency should be so high that while I am there at that location, I transmit at least one signal completely. And the signal is not distorted. And ideally, as many signals as possible, the complete signals. So they are being received here. But technically speaking, if somebody says, fine, I mean, that is a momentary, your momentary location is there. You can only transmit a unique P. You cannot transmit a complete signal staying back at that position because you are moving. That is actually the right way of thinking. So if there is no supposition, then this is also not possible. Ultimately, the right idea can happen when I talk about movement of pulses in a linear manner. Here, it's fine because of the whatever pulse I am transmitting, because of my motion or his motion, the size of the pulse, the amplitude, those things can change. But at least I will emit the complete pulse, and he will also observe it or accept it or absorb it completely, the full pulse, which is not the case in 2D pattern, because he will keep on changing the location, so he may not receive the complete pulse. That idea should always be there in your mind. Otherwise, what is the right way of looking into it? He can definitely talk about the apparent time period, even if he doesn't consider that, because then how the problem changes, it becomes more of a problem of kinematics, which is actually the right way of looking into things. Then I will simply say that wherever I am, and so from every position, I am just throwing balls. And that I am doing at a unique rate. And assuming that there is gravity-free space, I am throwing balls at in all the directions from that point. I mean, assuming spherical symmetry at some rate. So from a position I throw, then after some time I throw. So these balls are getting scattered. And out of these balls, a guy who is moving on a straight line will have impact of few of the balls. But the two consecutive impacts that will happen to his body will have a time deficit. And that is the apparent time period of receiving the signal, basically. And you understand that all that I have written on this page is not going to hold there. Try to understand what I'm saying again. I am saying with appropriate assumptions, I have written everything on the board. The concept, how should the concept be? Concept should be like this, because at a given instance, I cannot emit a complete pulse. So whatever I can emit is a unique value. And for the next value, I have to change my position. So generally, then how should we talk about Doppler effect in 2D? Then convert this problem, try to talk about the starting. Let's say I talked about a signal as a starting point. So I am throwing a ball, which is a starting point of signal in all the possible directions. It is traveling at the wave speed. And then after every time period, I am again throwing the balls. So actually in between also I'm throwing the signals, but just to interpret the starting and the ending point, I'm showing the dispersal of those two balls. And they are consecutively being spread from this point. And the guy who's moving on that line, the observer, will receive these signals. That is the zero wala signal. At some position he will receive sometime. And the next consecutive he will receive. And try to understand that the next consecutive that he will receive may not be the next consecutive that I have thrown. Because as I am moving forward and I'm throwing signals, you understand that the more closer I will keep coming, the signal from that place, which is maybe the third signal, would have been the second consecutive impact there. So it starts becoming complex then. So you understand what we are trying to do. This hassle of defining the apparent time period. To overcome this hassle, either we are working in 1D, where we are talking about the consecutive signals which are directly getting received by that person who is coming from front or going away from me. Or in 2D, we are assuming that I'm throwing it at such a dynamic rate from a given position that for a unique position, for every unique position on that line, I have already thrown something, and that he will receive after some time. So, I mean, there are so many combinations which are being formed on these ideas. That is where we need to, what I was trying to explain to all of you theoretically was the limitation of this concept that we generally use. Anybody who analyzes the problem for acceleration in 1D, he understands the concept of Doppler's effect, and there is simple kinematics which is present in Doppler effect, which we need to understand. I think all of you must have understood the idea. So this is also not the right way of looking into things. This is correct only after certain supposition. It should be known to all of you.
Just a small doubt on the actual question that we had. In the example that we were discussing, okay, so let me just start with the first one. When a body,
there's some issue with some echo or.
Sir, is it audible clearly now?
Actually, that was not very clear. It was kind of broken.
Yeah, sure. In the question which we were discussing about the circle and the receiver. So in that, when the receiver, when the source is moving away from the receiver, we can say that the apparent frequency to the receiver is less than the actual frequency, right, sir? So won't the path where the frequency is less than the apparent frequency be half of the entire circumference?
For all these positions, I will explain it. For all these positions from here to here, for any position which will come in between, if I connect the detector with this point and whichever direction I'm moving, as this vector makes an acute angle here, right? So what we are trying to say in this case was, for this patch, while you are moving towards him, you will generate a frequency which is greater than the actual frequency, that is from
Exactly.
A point to, let's say, point P.
Uh-huh.
A to P, your apparent frequency will be greater than the actual frequency, right?
Right.
And P to B, it will be less than the actual frequency. So P to B, a new apparent is less than the actual, and this is greater than the actual. And what else? We were discussing from B to further. Further, for all these positions, let's see, how do we observe all these positions? Again, let's call this point as Q. So B to Q, again, what is happening?
The
All
frequency
these,
will be less than the apparent frequency, actual
B
frequency.
to, yeah, very right. Because B to Q, wherever you are, all these
Uh-huh.
angles are obtuse. So B to Q, again, new apparent is less than the
Less
actual one.
than the actual frequency, right?
And here all the angles are again acute, no? So Q to A, as you will come towards this point, and generally I can say I am moving here, these angles are acute, that works. So Q to A, again, I can say that new apparent will be greater than
the
actual
actual frequency.
Yeah, that is right.
Right.
So
So
what
in the
was the what is
the part where the frequency is less than the actual frequency.
okay? So where is this less than the actual frequency? So A to P,
From
you can consider
A to Q.
less than चाहिए ना, क्या चाहिए? Less than 1000. Okay. So P to B, I suppose, and B to Q.
Yeah, right. Sorry, P to Q.
P to B and B to Q, that is one span where it is coming out to be less than the actual frequency. And if it is less than actual frequency, then you consider it as idle,
Detected by the receiver.
So then it is very simple. It will become half, I suppose. Eh? Yeah.
Yeah.
So it will become half idle and half active. Just check it for a moment. P to B, fine. Basically, the only thing that I have to check is, that is what I was trying to explain also, that angle should be like obtuse. If it is obtuse, it will be less. And that angle being acute there, then it will be more than the actual frequency, assuming the same thing, that frequency is high. No, it's fine.
So rather than the angles, can we consider the velocity? If the velocity of the source is towards or away from the receiver, like the component of its velocity on the line joining these two objects.
I mean, if the detector is always in a state of rest, and irrespective of the position, so I mean, with respect to D, wherever I am, if the line connecting the detector and the source, I have some velocity of source and detector being fixed. If this angle is acute, this is less than 90 degree, and I am towards the detector, basically he is going to observe a frequency which is greater than the
more than the actual frequency, right?
And whenever I am, so again the same things, no? The same ideas which we are. We are always thinking like that, that whatever is traveling, that is traveling at a high rate. And obviously what I have transmitted for him from this position will not be received at that instance. It will be received afterwards. But the apparent which has been thrown from this location, the rate at which balls have been thrown for him from this location, that will be received by him. Maybe I'm not at that same position when he's receiving that frequency.
Right.
So that is how we observe the question. So basically towards him, it will increase, and if I am away from him, it is going to decrease.
Decrease. Right. Thank you.
Right. So, okay. So let's take one problem. We have just worked on this, or wavelength pe bhi baat karte hain. So let us try to find out, solve this problem, because we were on Doppler. To Doppler and apparent wavelength, let us try to explain both. I'll give you 2 minutes to think over the problem. There is a plain sound signal. Go through this problem. There is a plain sound wave of frequency f naught, right? And wavelength in this problem, in this question. Yeah. So plane sound wave of frequency f naught and wavelength lambda naught travels horizontally towards the right direction. It strikes and is reflected from a large, rigid vertical plane surface perpendicular to the direction of propagation of the wave and moving towards left with a speed of v. So that observer is also moving towards left with a speed of v. So I have f naught, lambda naught, and this is all given to me. Now the question is, how many positive wave crests strike the surface in a time interval t? That surface is also moving. At the end of this time interval, how far to the left of the surface is the wave that was reflected at the beginning of the interval? What is the wavelength of reflected waves? What is the frequency in terms of f naught? And if there is a listener at rest at the left of the moving surface, describe the sensation of sound that he hears as a result of combined effort of the incident and the reflected wave trains. So let us try to write this first part. All these problems which I look upon, I just observe the kinematics of the problem and solve it. So let's see. क्या होना चाहिए? Lambda naught f naught is the actual speed of sound signal with which it is traveling towards right. Lambda naught f naught. So you can see that c term is known to us, and only a sound signal is traveling, and a large wall is traveling in the leftward direction with v. So how many positive wave crests will strike it in time interval t? So basically think about the number of signals that he has transmitted in t. Just look upon that number that he has transmitted in t. So seems like v plus lambda naught f naught upon lambda naught, right? And this whole multiplied by t. Check that. Because ultimately I am looking into the distance, right? Or agar this wall himself is traveling at v, and I am traveling, that signal is traveling at a speed of c, and c is lambda naught f naught. So relatively the distance that we have traveled in t time is this. This is the relative velocity, v plus c into t, the distance. And whatever signal is like, I mean, how much I will travel, and I've just divided that by lambda naught, because that is the distance between two consecutive positive wave crests. So I've found out the relative velocity into t, so that relative displacement, now divided by lambda. I think you understand. The number of positive crests that will strike the surface in time interval t. So answer for A part is v plus lambda naught f naught whole into t divided by lambda. Okay, let's go to B part of the problem. Here he says at the end of this interval, how far to the left of the surface? That was straightforward, because whatever would have struck at t is equal to 0, he has again traveled left, and that guy is coming from the rear side with v. So how far to the left he is? So I think this is t multiplied by that relative velocity again, and that seems to be lambda naught f naught minus v. So he will travel with lambda naught f naught, c, and he's traveling with v. So that distance is lambda naught f naught minus v into t. Okay. C part, he says, what is the wavelength of the reflected waves in terms of lambda naught? Now there are two ways to look into it. We can write the apparent frequency which is reflected, and then apparent, once we get the apparent frequency and speed we know, that will remain the same. So basically, the factor which with the apparent frequency is getting multiplied, the apparent lambda will get multiplied by the reciprocal factor. That is one way of looking into it. Otherwise, also we can observe. Just think about it and let me know how will you observe it. Answer is fine. I mean, I want all of you to think about apparent wavelength in different ways. I mean, see, like lambda naught f naught minus v upon lambda naught f naught plus v into lambda naught, that should be the correct result. I've just taken that factor of lambda naught f naught minus v upon lambda naught f naught plus v. You understand that this for me is the reciprocal of this factor is the reflected apparent frequency factor. And I've just taken that factor from there and multiplied by lambda. One more way of looking into the wavelength of the reflected wave is you look into the kinematics of the problem. Somebody can say, fine, let's say t is equal to, I'm just trying to explain C part, t is equal to 0. Let's say it's the starting of that pulse which was like if this was the pulse pattern which was moving rightwards. Right. If you just look into the C part, I think the first way of observing the answer is clear to all of you. Here, through the apparent frequency term, I have directly written, and I know because already I know that D part of this problem is actually F naught into lambda naught F naught plus V upon lambda naught F naught minus V. That is the D part to the problem. Just by virtue of that result, I have written this. And इसको मैं एक और तरीके से भी explain कर दूंगा, don't worry about that. And E part of the problem, here he says that if a listener is at rest on the left of the moving surface and describe the sensation of sound, that we understand there will be formation of beats there because you will observe those two frequencies, the F naught and this. So basically this is F naught minus F naught into lambda naught F naught plus V upon lambda naught F naught minus V, the whole mod of that. Now just think about the apparent wavelength which is being reflected. Try to explain this term to me. I mean, this term. Write it as lambda naught into C minus V upon C plus. Actually, you all understand that when the pulse is reaching that wall, if I am originally spreading lambda, that lambda which should have reached in time lambda upon C is now reaching in lesser time, which is lambda naught upon C plus V. I observe it like this only. वो पहुंच जाएगा lambda naught upon C plus V time में. So my complete pattern, one pattern is reaching in this time, not in the time period. And now obviously that pattern is now reflected back. So ideally he should have traveled C into this thing, C into this time. But the problem is, while my pattern is coming back, the wall himself is traveling at V. So the distance between the starting and the ending of my pattern, the complete pulse, will get reduced by a factor of C minus V. So basically C minus V into time. That is why that factor comes C minus V, and that is why this factor comes C plus. Very simple way of observing apparent wavelengths. So you will have a...
Sir, could you explain that once again?
I said, if an original pattern is moving, nothing is moving, the source is at rest, wall is at rest, the pattern is having a one pattern wavelet, wave train, has got a length of lambda naught. Now that guy starts moving towards me, the wall. The point is the pattern is moving, the front of the pattern hits the wall. So if you just look into one pulse, what is the time in which the complete pulse will get absorbed? That time is the length of the pulse. And why this term C plus V? Because the pulse is traveling at C and the wall is traveling at V. So the complete lambda naught will be covered in time, lambda naught upon C plus V. Fine. Now comes what wavelength I am going to get back. So the front will start moving immediately, and the rear, but by the time the rearmost part will start moving, the wall would have already traveled V forward. So the distance from the wall, that is the distance between the front and the end of the pulse, where the end is just touching the wall, is basically not Ct, it is C minus V into T. Because he is also moving forward a distance of Vt. That is how you look into apparent wavelengths. So what I wanted to explain in this question is, please don't observe apparent wavelengths like the extension to Doppler effect. Rather, just apply the kinematics and try to understand the length of the pattern. That is the wavelength. Whether it is going forward, coming back, or so on and so forth. I'll take one question which is more pronounced on the same idea in the next class, which is just based on apparent wavelength only, with more combinations of wind and observer and a lot of things happening. Just to explain this idea more, which was my main interest in this question. So fine, I have some classes actually, so I will have to finish it off here. I'll see you tomorrow again with some more combinations based on waves. Right? So take care and see you tomorrow, students. Bye-bye.
Thank you, sir.